I am struggling to make these videos because my laptop is really dying and the new one has not arrived yet. So it'll soon start making some weird noise. But nonetheless, let's see if we can make one podcast. So here is our salinity again. Let's focus a little bit more on the Gin Seas, Greenland, Iceland, Norwegian seas. With this extension of high salinity water associated with the extension of very warm water, relatively speaking, from the Gulf Stream, North Atlantic current, and so on. And in the Labrador Sea as well, you see that salinity is higher than the North Pacific, for example, even though it's a little bit lower than the North Atlantic. It's not so obvious here in the Weddell Sea, but still it's higher than the North Pacific. High salinity, of course, is favorable for increasing density with the heat loss. You can see the heat losses here in the Labrador Sea and the North Atlantic Gin Seas. This is the annual mean. Obviously, you have to look at fall and winter months, which will be even stronger. You get very high heat losses here from the ocean with a cold Arctic air blasting by here and very strong jets forming with the Greenland glacier having all kinds of impacts over here. And you can see that it's not so negative out of the ocean here except in the Kuroshio. Data is always a problem here in the Southern Ocean. Nonetheless, we can also look at evaporation, precipitation, and E minus P here. If E minus P is positive, that's always a good sign. Means it's basically an evaporative region which increases salinity. So it's just consistent with the salinity we saw already. And the other thing to look at is, of course, mixed layer depths. So here you can see in the Labrador Sea and the Gin Seas, the mixed layer depths are somewhere in the 800 to 1000 meters or greater. But at these latitudes, mixed layer is not always a very well defined concept because you have density gradient that is greatly reduced, as we'll see with stratification, but you can have winds and wind shear close to the surface. So if we stick to the definition of density homogenization in the vertical as a definition of mixed layer, then a deep mixed layer indicates easier sinking of the water masses from the surface if there is a buoyancy loss. So we've already talked about high salinity, negative heat fluxes, which means heat flux out of the ocean according to this convention here. That can create loss of buoyancy and sink the waters easily. Lack of stratification is the same thing. So you can just look at stratification as a measure as well as N over FREF, where FREF is some reference value of Coriolis parameter, FREF of 10 to the minus 4 per second over here, which is a value at some mid-latitude location. Here we are with the deep water formation sites in the Gin Seas, Labrador Sea, and the Mediterranean intermediate water forms a part of the MOC as well as it comes out here. And at some point it can actually be heavier than the Antarctic bottom water, but it then mixes quickly with the rest of the Atlantic Ocean. And there is the Weddell Sea. Ross Sea is not shown here. So stratification is very strong in regions where you have a lot of solar heating, like in the low latitudes. Stratification gets in this measure weaker, but you have to be careful because we are using a FREF. Nonetheless, warm waters, strong stratification; colder waters, weaker stratification. And we have fairly weak stratification in the North Atlantic Gin Seas and the Labrador Sea, as well as here in the Weddell Seas. So just to kind of continue the story, everything seems favorable for buoyancy loss to create convection and sinking of surface waters in these locations. But you have to get a sense of the scales here. Just the water sinking at these few places is going to fill up the entire deep ocean. So obviously we have to see the intensity of the sinking, the time scales, and so on, which we will do. And that's the net upward heat flux again, clearly showing heat losses in the annual mean. Not so obvious here, as I said before. So if you look at the stratification n squared minus g over rho ref d sigma dz, we will stick to temperature as a measure here, approximating the d sigma dz with g alpha t dt dz. And this is again showing the potential density we have looked at several times for the top 1 kilometer and for the whole water column. You can clearly see the doming here, and you can see the lack of stratification dt dz here, which is created by deep water sinking but also favors deep water formation or buoyancy loss and convection. Ekman pumping is also a favorable where it is negative, you have water being pushed down. Where it's positive, you have water being pulled up. You can think of that as just in terms of E minus P and buoyancy loss and the whole mixed layer physics, etc. So I don't want to emphasize too much the Ekman pumping and Ekman suction here, because if the mixed layers are several hundred meters deep, then whatever vertical motion is happening at the bottom of this deep mixed layer is not that critical. But if you have strong wind stress curl, then near surface wind shear can create favorable conditions for deep water formation as well. Wind shear is basically energy available for mixing, right? So the ship Woods Hole's Nor went into the Labrador Sea during the fall winter months of 1996 and 1997. You can see this massive wave coming towards the ship here, and the cold, miserable temperatures freeze everything on deck, but it has to be cleared up for instrumentation and so on. So these hardy souls are out here breaking the ice in this harsh winter. The data collected from this cruise is really phenomenal, showing us the deep water formation, which we will see in the next podcast.